Rejected. Okay. So last time we talked about two generative models, variational autoencoder and GANs, a little bit. Uh, and today we'll talk about state-of-the-art generative models, diffusion models. And we'll look at three approaches: score matching through variational autoencoder, and just mention the stochastic differential equation because we won't have time to cover the stochastic differential equations in depth. So I think you didn't hear before about Markov chain Monte Carlo methods, except David, who took last year independent study on Bayesian deep learning. So the particular case of Hamiltonian Monte Carlo methods for sampling from arbitrary distribution, in our case, distribution is given by images, is so-called Langevin dynamics. And the formula for Langevin dynamics looks as follows. We take one image, for example, from our data set, and then we calculate the next point as the previous one, plus this additional term. And you can think about this additional term as the moving in the direction of the highest probability density. So, and there are two processes. One process kind of forces to generate images or whatever your data set is from the mode of your distribution with highest value of probability density. And the second process doesn't allow you to converge actually to this mode because it adds every time some noise. And if the sampling in this Langevin dynamics looks as follows. We'll start with some x. It can be a sample from your data set. It can be just arbitrary numbers. And then you iteratively apply this formula. And after maybe 500 steps, we will converge to the higher value of the probability. So we will disregard all previous samples and we will accept only the sample with high number, like 500 or 1000. So yeah, the first problem is that we don't have actually the expression for probability density in images. We have just images, samples. The second problem is that it's kind of a waste of time to generate many samples and then take only the last one. The other problem, I will mention this now, I want to visualize this process. So if you look at the minimization problem, then you remember we go in the direction of anti-gradient. Then it's called gradient flow. Then it will look as this smooth red line on the surface of our loss function. If we add this noisy term, and this is called stochastic gradient, stochastic differential equation, or Langevin equation, then it adds the noise, and you can see it kind of prevents our stochastic gradient descent from convergence to the real minimum of our loss function. And so you can think about stochastic gradient descent as a sampling from some distribution with Langevin dynamics that, on one hand, moves your next point to the region with highest probability density. On another hand, it adds noise, so it prevents from generation of this images from the same point. Um, so let me mention the other problem with this method. So if we have some distribution, multimodal distribution, and if we have two modes, it's multimodal, then in theory, Langevin dynamics will sample from all the modes of your distribution, but if time goes to infinity. So in practice, if you start samples at one point, it actually will stack in this mode. So this is another problem with Langevin dynamics sampling. So now let's look at the consider another approach for sampling. Let's see. I will draw first the image. Now let's consider a little slightly different approach. So let's say we have the multimodal distribution, some very complex distribution, and we want to sample data from a known distribution that is built in a torch, for example, standard Gaussian distribution. And let's denote this space by x0. So P0 stands for this complex distribution of our data. And then we will kind of what's called destruct when we add noise with kind of yeah, but we'll kind of destruct our image, or what is the correct word? This, no, when we damage an image. Okay, so we will add yeah, distort and kind of damage our image, add in some noise. So, for example, x1 will be represented as so we take as a number smaller than 1, and we will add let me see to be yeah, I'm using better. So we will add so we will take our image x0, multiply by some number smaller than 1, and add a noise with factor square root of beta. So what it does, and typically beta is very small, so 1 minus beta will be large. So it means that new point x1 will be very close to original image. And also, if you look at the variance of standard Gaussian is 1, and the variance here will be multiplied by 1 minus beta. So it's called variance preserving scheme, because if you calculate the variance of x1, it will be the same as variance of x0, because it will be 1 minus beta times 1 plus beta. So beta will cancel out. As the result, you will get a distribution which is very close to the original one, but it's a little bit smoother than original distribution because we kind of added a random noise. And then we continue this process, and on every step, we will make our images more similar to noise. And here we will have almost normal distribution. So this is how it looks in formulas. So on every step, we multiply our image by a constant smaller than 1 and add noise also multiplied by a constant smaller than, such that these constants, the squares sum up to 1. Then, if you apply recursion, you can actually prove that your sample at time t plus 1 can be represented through the original image x0. But the mean and variance will look as follows. So on the next slide, I actually provide the proof. It's just by induction. So you can show that the formula for x at time step t plus 1 through x0, through the original image. And where is it? So it will look as follows. It will be square root of alpha times x0 plus square root of 1 minus alpha bar times the noise on the current step. And if we take the product of numbers, so alpha is the product of 1 minus betas, so it's the product of numbers smaller than 1. And if you take the product of numbers smaller than 1, even maybe 20 numbers, you know that the result will be very close to 0. In other words, if you take, for example, if you make 1,000 steps, then your image will have almost 0 mean. And this value will be close to 1. In other words, it will be almost standard Gaussian distribution. So after you apply this process 1,000 times, you will converge to a standard Gaussian distribution. And then the sampling process will look as follows. So we'll apply Langevin dynamics, but now we will apply Langevin dynamics in between very close distributions, because you remember the problem with staying in one mode. Now, if we just take a sample from normal Gaussian distribution, so we will denote this time by T capital, which is just normal distribution. This time will be T minus 1. This distribution at time 1, this distribution at time 2. So we organized our sampling process as follows. We have distribution on x1 given x0, because x1 is calculated through x0 plus noise. Then we calculate distribution of x2 given x1 and so on. And these distributions Q are normal distributions. They are just given by this formula. These are Gaussian distributions. And so when we move in this direction, we kind of add noise to our image. And in the end, we get just the image with noise that has a standard Gaussian distribution. Now, if you want to sample, we will apply Langevin dynamics and we will perform different steps. So, for example, we will sample 2 samples. We will accept the sample here, and then we will get the sample from distribution at time t minus 1. And because our distributions separated just one step are very close to each other, then it's not anymore a problem that we will stack at one mode, because now we will continue, for example, here perform these steps of Langevin samplings, and we will move, for example, here. We will perform samplings here. We will move maybe here. Then we will perform steps here. Maybe we will move here, and we will end up at this mode. If you start, for example, with sample here and perform several steps of Langevin dynamics, you can move here. Then you perform several steps of Langevin dynamics. You may move here. And in the end, you will end up maybe in the different mode. So again, you remember the problem was to cover the entire distribution of our images. And GANs, they suffered from mode collapse. So they sampled images from one mode, the same standard Langevin dynamics. But if we organize this kind of diffusion process, when we add noise and we distort our image by a small amount of noise, then on every step, closed distributions, we will have closed distributions, and we will get samples at the close distances. But because we perform many steps, we can end up in different modes. So this is the main idea. So the process looks as follows. We start with noise, pure noise. Then we perform m steps of Langevin dynamics, and in practice we take just one step because distributions are very close, so we don't need to warm up our Markov chain. And we repeat this process t capital times, and as the result, we return the image. So it looks great. The only problem is that we don't know the distribution of p. So we can't apply this method because we don't know distribution of p. We just have the samples. And the rest of my lecture will be about how to estimate this distribution. So the first approach to estimate this distribution is called score matching. So in probability theory, if we have the distribution that depends on some parameters, theta, let me use, I don't know, some parameters, theta. The gradient with respect to parameters is called score function. In diffusion models, we take the gradient with respect to x. And I think by mistake, they call this score. But now, when we talk about in machine learning, by score, now we mean the derivative with respect to x, but not as the common definition of the score in statistics, where the derivative was with respect to the parameters. And let's introduce a neural network. A neural network with weights theta, which will approximate this gradient of the log of the probability density, or the score in, as it's used in machine learning in this diffusion models literature. And how to estimate our neural network? We will we want to approximate with our neural network this score. So it looks good. So this is just the average mean squared error. But the problem is still the same. We don't know the target, the second term. And now we will do a little bit math and find a way to train our neural network. So a little bit of math. So this is our target. We want to train neural network to approximate this score, but we don't know this score. First, let's take the square. So it will be the square of the first term minus 2 times the first times second, plus the square of the second term. But the second term doesn't depend on theta, so I just denote this as plus constant. Then we will take a derivative of the logarithm, and derivative of the logarithm is 1 over p times the derivative of p. And you can see that p will cancel out. The next step, because we have this lemma, the formula that relates x at time t and original image x0, we can actually use the marginalization idea. So we can calculate the probability of x and x0 and integrate over x0, we will get the probability of x. So I will substitute now this p under the derivative by this integral, which is the marginal probability of the joint probability on x and x0. And because p of x0 doesn't depend on x, we can factor out p of x0. So what I'm doing next? Yes, I just okay. Here I just change the order of integration and differentiation, and then I factor out next. Okay. I use the log derivative trick again because the derivative of the log, so the derivative of our q, if we calculate the derivative of the log of q, it will be 1 over q times derivative of the q. And it means that derivative of the q will be derivative of the log times q. So I just use instead of derivative of q this trick. It's the same as derivative of log times q. And then we add and subtract to complete the full squares the square of this term. So we add and subtract. As the result, we have the complete squares here. It will be MSE between S and the derivative of this Q, plus this term doesn't depend on theta, so we use this, denote this as constant. And now we rid of P distribution, we just have the distribution of the images, 0. And this distribution actually has the normal distribution. We know this expression for this distribution. The only problem is remains to calculate the integral. And I believe we talked about Monte Carlo estimation last time. So instead of, we will replace integral with the sum, and we will just sample x0 from our data set. So we will rid of the p. I believe it's my next slide. Oh no. Okay. So we can to calculate this integral, we can use Monte Carlo estimation, and then we will rid of this probability, and we will just use samples from our data set. We'll just use images. So this is how we can train a neural network that approximates this gradient of log of probability, and then we can apply our Langevin dynamic steps. So this was the first approach. The paper was called uh, score matching. In practice, we use another approach through the model with latent variables. You remember last time? So what are the latent variables in our case? What we can observe in our data? We can observe only images. So all other distributions, all other x's, we will treat as latent variables, as unobserved variables. And you remember in variational autoencoder, we had one latent variable z. Now we will have t minus 1, let's see, t, because I begin with 0, t latent variables. And we can write our incomplete log likelihood like we did last time. And as you remember, we estimated incomplete likelihood with evidence lower bound. So we had this Elba and Kyle divergence, and we estimated with evidence lower bound. So let's write this evidence lower bound. So it looks as follows. This notation means that here is a vector of random variables x1, x2, and so on, xt capital. So just to make shorter the notation. So as you remember, our distribution on the process when we add noise, it was Markovian. It means that it depends only on the previous step. So we can rewrite this distribution as the product of Q with x1 conditioned on x0 times Q of x2 conditioned on x1 and so on. What's called chain rule probabilities. And the same with numerator. So then we can split this logarithm of the product into the sum of logarithms. And if you look at this expression, it will be an integral of q times log p over q. It looks similar to Kyle divergence, but not yet. So and also kind of variables, they flipped in numerator and denominator. To change the order of variables, we will apply the conditional probability formula. So I will express this denominator. It doesn't depend on x0 because it's Markovian property, but we will just add x0 and write formally the joint distribution on t and t minus 1 over the condition. And the joint distribution can be expressed as conditional times the condition again. And after this manipulation, we will substitute this instead of q. And after we substitute this, we will split our sum into two terms. So now the order of the variables will be the same. And it will be Kyle divergence. So on the next slide, So let's maybe skip all these derivations. We can show that this term is just the Kyle divergence between these two distributions. So, and as you remember, Kyle divergence between two normal distributions has a closed form expression. So let's see if I have this. Yes. So so because our distributions Q were normal, we can calculate actually mean and variance for this distribution, and it will look so. So I don't want to do this math now, but it follows from our expression for xt via x0. So you remember we proved this lemma, how xt can be represented through x0. So if you solve this with respect to x0, you can actually get this expression. Okay, so everything that we denote by Q, everything is known because we organize this process. The problem is how to learn the process, the backward process with P, which we denote by P theta. And we will look for this backward process in the same form as our forward process. The only problem is that when we add noise, we actually have information about image. When we want to do the backwards process, we don't have information about our image. And we will denote the image, like here image was x0, we will denote by a neural network. So we'll ask neural network to learn the image from the current time step. And this assumption that backward process also has a normal distribution will allow us to use the explicit formula for Kyle divergence, which is the square difference between means. So U tilde has explicit formula from our forward process, and mu theta is the neural network. So, and finally, we have the loss function that we will use to train our neural network. So this means we can calculate explicitly using the image with noise and original image. This mean is our neural network. Okay, so it should be multiplication sign here. Because mean is connected with x, we can express x through mean, and then we will get the, instead of difference between mu, you can use difference. So you will get a factor here between x's. But in practice, we use actually the difference between the noise, because as you remember, our process looks as follows: x t plus 1 equals square root of 1 minus beta x t plus noise. So if you know x, you can express epsilon. So if you express epsilon from x, then you will get another factor. And in practice, we will force our neural network to estimate not the original image from the time step t, but the noise that was added to image to get the distorted image at time 10. So this is the main idea. In practice, if you will use this factor, your neural network won't be learning. In practice, we use simplified loss without these factors. I won't explain why it won't be learning. And now the process looks as follows. If we train our neural network, we can sample noise, just random noise, and then estimate original image from time step t, then from time step t minus 1, from time step t minus 2, and then we will reach our time step 0, and we will return the image. So this process is called denoising. For training, we have an image. We take an image or batch of images. We sample time, and then I didn't say. So how we add time in our neural network? We just create an embedding, and it goes as typically we use the same embedding as in transformers with cosines and sines. So we sample time step, then add this time step in our neural network. Our neural network will estimate. Also, we sample noise, and then we calculate x based on this formula. Now we have our input image, and we also add noise. And when we have the estimation for xt, we can minimize the difference between xt hat and xt, or between the epsilons, because on the previous slide, you saw that difference between x's is the same as the difference between epsilons. But you can see also this from this formula. Difference between x's is the same the difference between epsilon. But one epsilon is known, another epsilon is a neural network. Okay, and now what is the connection between score matching and the latent variables model? So, because our process has normal distribution, we can take log. You remember, normal distribution is e power negative square difference. So log of e will cancel out, and we will get just the power of our e. And then we take the derivative, and derivative of the square will give us 2, 2 will cancel out. And if you compare this expression with expression for epsilon, you can just solve this equation for epsilon. You will notice that they are very similar. So they coincide with up to just factor of square root of 1 minus alpha. And this is the connection between score. So to learn epsilon neural network is equivalent to learning score function. Okay, the last approach is through differential stochastic differential equations. So the previous approach was using discrete stochastic process or Markov chain. Um, so if we look at this problem from this point of view, like if we create very, very, very many time steps, then our trajectory will look almost continuous. So the third point of view on this diffusion models is from the continuous process point of view. And there is a theorem. So, okay, we have two model distribution, and we have a process that results in simple distribution. And this process has explicit notation, explicit formula. So if we apply Taylor's expansion, the square root will give us 1 minus 1/2 beta cxt. So we multiply by xt. And if we take this xt to the other side, we will get the difference between x's. And the difference between x's can be considered as dx. So we will have dx at time t equals to 1 minus 2 beta times xt d t plus square root of beta t and here we will have also dt under the square root epsilon, and this term is typically denoted actually is denoted by the derivative of Wiener process. So from our discrete process, we can go to the continuous process. And if we know the function f, in this case, it's just 1 minus negative 1/2 beta. We know our function g, in our case, is just square root of beta. There is a theorem that there is an equation that describes the reverse process. And the reverse process, you can see, uses this core function. So why do we need three approaches? So in score matching, it's used in classifier guidance. I don't think I have time to introduce this today. The model with latent variables, it allows us to use a different noise process. So instead of normal distribution, we can use arbitrary distribution. So it's allows us to build different models. And the point of view from stochastic differential equations, because we have explicit formula for equation, we actually can solve this equation. We can solve with respect to p, and we can get the estimation on p. And in practice, also, if we solve just ordinary differential equation without noise, we can find the original image much faster. And this method is called DDIM. uh, deterministic differentiable inverse model. So it's used for faster sampling. So instead of going back and evaluating 1,000 samples, we can solve an ordinary differential equations, which typically requires about 30 steps, and get the image. Okay, I think I have actually one slide left. If what do you think? Should we finish? I wanted to introduce the stable diffusion. So you have class, you can maybe go. So now, what if we want to generate not general images, but images from the specific class, like dogs or in MNIST specific digits. So it's called conditional diffusion model. And instead of have access to our probability density, I want to have the access to the conditional probability density. And here we will use the, again, conditional probability formula, that is the joint distribution over condition. The joint distribution I can write as the conditional times condition over condition. And the log of the product is the sum of logs, sum of logs. So the first, so the second derivative is our score. If you look at the this term, our score. The first derivative is the probability of class given X. So you can use another neural network like discriminator that predicts a class for image. It takes as input image and predicts the class of this image. And that's why it's called classifier guidance. And the only problem that you can't use pre-trained neural network because you need to have a neural network that predicts class for noisy images, not only for clear images, but also for noisy images. So in practice, typically people add noise and then train this classifier for every step. And the second approach is to use classifier-free guidance. So in this approach, we need pairs of X and targets. You can think about this text and image if we talk about text to image problem. And then pass to your neural network not only embedding of time, but also embedding of the class. And also the empty class, like empty string. So your neural network will try to approximate images based on also the label. And if you pass empty label, then it will work as just standard diffusion model. It will just generate different images. And the main paper that I want to talk about is the image synthesis with latent diffusion. Although this is the name of the paper, it's known as stable diffusion. I don't know why. The paper is called latent diffusion. So the idea of this paper is all in this one image. So first we train autoencoder, variational autoencoder that we talked about last time. You remember, variational autoencoder takes in as input image and then generates an image. Then So this encoder and decoder, this is pre-trained autoencoder. It can be a variational autoencoder. In DALI, it's vector quantized autoencoder. So in a variational autoencoder, we map our image into latent representation. And then in the latent representation, we will actually start the diffusion model. Diffusion process that takes thousands of steps. Forward, it adds noise and then it removes noise. And if you want to apply also conditioning, so without these transformers, it would look like a standard diffusion process, but in smaller dimension space. If we want to use idea of classify free guidance, when we add also condition, then they proposed to in standard classify free guidance, we just add condition as embedding, like one hot encoder or cosine and sine as time. But for texts, they proposed to use this embeddings of text. So this is the last draw that I will draw today. So we have a large image and we have a small image after encoder. Encoder just reduces the dimension. Then we also have a text. A text will be represented by embeddings of tokens. Oh, and I didn't mention, they use clip. That's why I talked about clip on Monday. So every token will be represented by a vector. Image, as you remember, after convolutions, it has also channels. So we will kind of unwrap this image into a long matrix. So this channel dimension will be the height of embeddings. So kind of every pixel on the image will be now represented by this vector. And now we apply cross attention between these two matrices. So this QKB stands for cross attention. So our queries will be image, our keys will be text. So we kind of will look from the image to the text and then apply after that self-attention. And because for images we use UNet, we will have this self and cross attention on different sizes of our image, because UNet applies convolutions and then max pooling, so it reduces the size and then increases the size. So, and this is the idea of this model. So it uses very short autoencoder with diffusion model in latent space, and condition is implemented not as just vector embedding, but as attention. And I think you all saw these images generated or from text. And this is, I believe, 2022. So now the quality, of course, is much better. So we have input text, and I like this one. Squirrel eating burger. Okay, I think we can finish our class at this point. So we know how to go through from images to text. Now you know how to go from text to images. And yeah, if you're interested in like other topics, sorry. Could you remind your name, please? Could you remind your name, please?
Steve.
See,
I was not.
were the guy who were interested in some forces and special and additional topics? No, because I have two students who
I added the generative speech.
speech.
Yes, from
Well,
hmm?
the speech like speech processing. Or?
Yes, speech.
Yeah. So yeah, we have two students who are interested in speech processing. So what do you want to do, guys? Do you want to meet during regular class or maybe separate another time?
Regular class would probably be easier. I'm fine anyway.
Okay. So what do you want to do? Do you want to so there are different tasks like speech recognition or speech generation. What are you interested in? Or in both?
For me, I kind of both, but I'd say more speech generation.
Same thing. I like both, but
It'd be interesting to look at
maybe speech generation.
It could be interesting to look at how the open source SESI model works.
I don't know that one, but probably I'd be into that.
It's a small 1 billion parameter model